I'm not always there.
Right, right.
All right, hi everyone. Welcome to the UAE Space Agency. Today's speaker is Dr. Manasvi Lingam. He got his PhD from the University of Texas at Austin. Then he did a postdoc at Princeton, then another one at Harvard University. And now he's an assistant professor of astrobiology, aerospace physics, and space sciences at the Florida Institute of Technology. So Manasvi, welcome to our center, and it's all yours.
Right. Yeah, thank you on everyone's behalf for having me, Dr. Atri. It's a pleasure to be here and to be speaking with all of you. I look forward to giving my presentation. And yeah, so from what I've gathered, this is going to be a very diverse audience. So I'm going to begin with a lot of preliminaries. There may be, many things that a lot of you are familiar with, and I won't be getting too much into the technical details, but I would be happy to chat later if time permits. So as the title indicates, I'm going to be speaking about some aspects of habitability mediated by stellar flares and space weather phenomena. And I would like to acknowledge a few of my collaborators, Avi Loeb from Harvard, Fei Dong from Princeton, and Andy Knoll from Harvard, and as well as a few others. And so this is going to be the general outline of the talk. First, I'll begin by sort of defining some of the basic concepts that we will be encountering in the later parts of the talk. And then I'll speak about how stellar flares and related phenomena impact atmospheric escape from exoplanets, how they impact prebiotic chemistry, which means basically how do these phenomena impact the formation of the biomolecular building blocks? And then I'll speak about the impact they have on ozone depletion and how that in turn could have impact on biospheres. And then lastly, if time permits, I'll speak a little bit about the risk to human societies as well. And so with that, let me get started. So first, this talk is one that is going to deal with astrobiology. So I always find it helpful to begin by briefly motivating what this is. And as the definition indicates, it's the study of origin, evolution, distribution, and future of life in the universe. This multidisciplinary field encompasses the search for habitable environments in our solar system and habitable environments outside our solar system. So, and therefore, as one can see, it includes a number of different fields. To begin with, astrobiology starts at home. So it sort of involves studying how life originated and evolved on Earth. As you can see from this panel here, it includes specific targets within our own solar system like Mars, and then the likes of Europa and Enceladus, which are typically called icy worlds. And then, of course, it involves the rapidly growing field of exoplanets, which is going to be more the focus of my talk, but not exclusively. And just to remind people what exoplanets are, this is the short version of extrasolar planets, which means planets outside our solar system. And the study of exoplanets is one of the rapidly growing fields in astrophysics and astrobiology. Currently, we know of more than 4,000 exoplanets, and this number is expected to grow very rapidly in the coming decade. So just to show you a couple of examples. So the first one is Proxima Centauri, which is the exoplanet that is nearest to Earth. It's a little over 4 light years away. It orbits Proxima Centauri, which is a star with 12% the mass of the Sun. The planet's mass is not precisely determined, but it's known to be greater than or equal to 1.27 times the mass of the Earth. And its semi-major axis is around 0.05 AU. And then the other notable discovery in the last few years, which I think a lot of you might have read about in the news is the TRAPPIST-1 planetary system, and this comprises of 7 Earth-sized planets orbiting the star TRAPPIST-1. And this TRAPPIST-1 is a very tiny star. As you can see over here, it has less than 10% the mass of the sun, and it's 40 light years away from Earth. And here are some of the basic properties of the planet shown, which I won't be getting into. And so the other thing that I want to mention is the habitable zone. This is one that, again, one sees in a lot of media outlets. So what is the habitable zone? It's essentially the region around the host star where liquid water could theoretically exist on the surface of a rocky planet. So it's known that about 10% of all stars in the Milky Way, give or take a factor of a few, have an Earth-sized planet in the habitable zone. So one thing I just want to emphasize is that habitability and the habitable zone are not really completely synonymous. You could have planets in the zone that are not habitable for other reasons, for example, not having an atmosphere and so on, or just experiencing very high radiation fluxes and so on, and vice versa. So why am I going to be talking about a lot of stellar phenomena? Because flares and so on are stellar phenomena. So habitability is defined as the potential of an environment to support life of any kind. So it's clearly a concept that pertains to planets and moons. So then the question is, why do we care about the characteristics of the host star at all? And a related question is, in other words, do the properties of the host star influence the prospects for the origin and evolution of life on planets and moons? So therefore, the goal of this talk is going to be to see why this is indeed the case. In other words, we will be focusing on flares and related phenomena such as coronal mass ejections and solar proton events, which I'll be getting to shortly hereafter. So this sort of completes the basics of the talk. And now we move on to the first thing that I want to discuss, namely atmospheric escape. Before I do that, let me just remind everyone briefly about what flares are. So flares, of course, are energetic explosions on the surface of the sun and other stars, and they're most commonly detected because they're accompanied by the emission of radiation in multiple bands, including the visible spectrum, in the ultraviolet, in X-rays, and gamma rays. And so the Kepler satellite, which was essentially launched in 2010 and functioned until a few years ago, enabled us to characterize flares on a very large number of stars because Kepler looked at something on the order of 100,000 stars. And this enabled us to gain some statistics to find out the number of stars that are subjected to frequent flaring as a function of the stellar mass. And as one can see, it generally increases as one moves towards lower mass. So K and M stars are the smallest mass stars, and they're also the most common. And one can see that the frequency is around 5% here, whereas for stars like the Sun, which are G-type stars, it's about a factor of 2 lower. So now the other thing that I want to mention is, as I said, I'll also be covering related phenomena. And flares are often, but not always, accompanied by the expulsion of large blobs of plasma from the surface of the sun. And these blobs carry large quantities of plasma and magnetic fields. They can transport kinetic energies of up to 10 to the power 28 joules and masses of up to 10 to the power 18 kilograms on active stars. And what you see in this picture here is an example of coronal mass ejection. The brighter shaded regions are essentially the plasma being expelled, and the white circle that you see in there is meant to be the star. So the coronal mass ejections can have a characteristic length scale that is larger than that of the star itself. So now, so of course, now what I'm going to be talking about here, as I mentioned, is atmospheric escape. And by atmospheric escape, I specifically mean escape of atmosphere from rocky Earth-like planets. And so how does atmospheric escape occur? Well, the first thing, the most obvious thing is that you need the particles to gain an energy that is more than the escape velocity of the planet. And that could happen in a number of ways. So here you have a schematic diagram showing how you could have particles with energy greater than V escape, sort of, escaping from the atmosphere, and those that don't would still be bound to the planet. And now, the energy the velocity that you need in order to escape the planet could be supplied through a number of different channels. It could happen through collisions where you have exchange of energy and some particles gain energy and then lose, and then, are therefore removed from the atmosphere. This is known as Jean's escape, and it has a history of more than 100 years ago. But then you can also have particles gaining energy, and therefore being accelerated, essentially having some kind of energy and momentum transfer, not just through collision, but also you could have when you put charged particles in electric fields. Of course, we all know that they would be accelerated, and they could therefore be subject to escape when in the presence of electromagnetic fields. And it's known that both stellar winds and coronal mass ejections are capable of driving atmospheric escape, through a number of non-thermal mechanisms. And by non-thermal, I mean essentially not involving collision. In order to study this problem, what you really have is either a coronal mass ejection or a solar wind or some other kind of phenomenon interacting with the planet's own atmosphere and magnetic field and so on. So essentially what you have is one mass of plasma coming from the star interacting with the planet, and therefore you need to use sophisticated multi-fluid MHD simulations. And the reason it's multi-fluid is that you're going to have a species within the atmosphere, you're going to have stellar wind protons and electrons, so it's therefore going to involve different species. And therefore, the question that I'll be posing here is, how do flares and coronal mass ejections impact escape rates, especially for planets around M-dwarfs? So first, before I get to M-dwarfs, I'm going to show you some simulations for an Earth-like planet orbiting a Sun-like star. So we still haven't gotten to M-dwarfs. And just to recall, M-dwarfs are the smallest stars. And, they typically have masses ranging from less than 10% to roughly 50% the mass of the Sun. But right now, I'm just going to be talking about a Sun-like star. And I'm going to be talking about a Sun-like star and an Earth-like planet. So what are water worlds? So it's believed that on some planets, you may have such a high inventory of water that you may have such a high inventory of water that most of your atmosphere is dominated by water vapor. So what you see over here is the number density of the escaping species, which is the water ion. And the white lines essentially indicate the field lines, and the color essentially reflects the contours. And so that's in the top column. That's the number density, and in the bottom column we have the pressure, the total pressure. And what we have over here is the first column over here, which is labeled current. You can see the number density and the total pressure for the current solar wind conditions. And what we see over here is for the early solar wind conditions, namely how the solar wind would have been around 4 billion years ago. And what we have over here is the number density of escaping particles and the total pressure for a large when a large coronal mass ejection impacts the Earth. And this is essentially labeled Carrington because in 1859 there was a large flare and an associated coronal mass ejection which impacted the Earth. And it's something that I'll be returning to later. This is an example of a large CME that could have occurred. And so what we see over here is the coronal mass ejection and the effects induced by it. So let me just move on to the next slide where we can see how, so what we see over here, this is the last column is the one that we should pay attention to, which gives us the escape rate from the planet in terms of the number of particles per second, or rather in this case, the number of ions per second. So you can see that for the current solar wind conditions, it's on the order of 10 to the power 26 particles per second. But when we go to a Carrington event, it goes up by nearly a factor of 100. And therefore, every time you have a coronal mass ejection impacting the planet, a combination of higher ramp pressure. So by ramp pressure, we essentially mean it's the product of the density times the square of the velocity, the mass density times the square of the velocity. So it's proportional to n and to the velocity v. So you can see that the number density is higher during a coronal mass ejection as is the velocity. And so therefore, a combination of both these factors are basically aiding in increasing this particular escape rate. And therefore, during coronal mass ejection, you can have the background escape rate of particles from the atmosphere being transiently boosted by a factor, by an order of magnitude or even more, depending on the size of the CME and other parameters. So in a similar vein, so now I'll move to M-dwarf exoplanets. And people, when they study M-dwarf exoplanets, it's quite common to use TRAPPIST-1 as a prototype because we have 7 planets in the system. So there's a lot of parameter space to explore. So what you see over here are the black dot, I mean, each of the dots essentially correspond to the TRAPPIST-1 planets. The lowest curve essentially corresponds to the escape rate for when you don't have any flare, you don't have any coronal mass ejection taking place. And whereas what we see over here, the middle two curves show what happens when you have only a flare but without an associated coronal mass ejection, or when you have a coronal mass ejection without a flare. And the topmost curve is the one where you have both of them at play. Again, you can see that there's a couple of orders of magnitude difference, or even more in some cases, between the case where there's no flare and no coronal mass ejection versus one where they are both. And these escape rates were computed for the TRAPPIST-1 planets with under the assumption that their atmospheres, if they exist, were roughly similar to that of Earth, or roughly similar to that of Earth, when subjected to a flare with energy 10 to the power 26 joules, and with coronal mass ejection that is commensurate with this flare energy. So that completes the first part. And I think the basic thing to sort of remember is that the atmospheric escape can be transiently increased by orders of magnitude due to flares and coronal mass ejection. And recently, there was a paper which I haven't put here, which tried to look at a rocky exoplanet known as LHS 3844b. And and observations suggest that that planet doesn't have an atmosphere, even though it's rocky, even though it's at a distance that is sort of in some ways comparable to that of Venus in terms of the stellar flux it receives, and yet it doesn't have an atmosphere. And the suspicion is that a combination of strong stellar winds as well as this kind of transient activity from flares and coronal mass ejections may have contributed to it losing the atmosphere. So now we get to the second part, namely the prebiotic chemistry. And before we get there, I just need to introduce a little bit more terminology. So what I'll be dealing with here is essentially what are known as solar or stellar proton events, which are SPEs. And these are essentially, so if you look at the figure over here, what you can see is there's energetic protons and ions that are essentially moving away along the magnetic field lines. And these energetic protons and electrons can be produced in two different ways. Firstly, they can be accelerated directly at the sites of the flare. So every time you have a flare occurring, by way of magnetic reconnection, you could have the magnetic energy being transformed into, for example, particle acceleration. And then they could also be accelerated by shock waves associated with CMEs. So there's two different sources, and they can both give rise to solar proton events. And so remember, these proton events are going to essentially, so these energetic protons and electrons are going to move along these field lines, and they're going to impact the Earth. And so in the same way as, say, ultraviolet radiation or any other radiation, if they impact the planet, for example, the Earth, it could also be Mars. So these essentially represent a source of energy. And so in the 1950s, there were some very famous experiments done using lightning as a source of energy. And what people did is they tried to simulate lightning in the laboratory, and they put a jar comprising of atmospheric gases, and then they sent an electrical discharge through it, and they found that a lot of the building blocks of life were synthesized in these experiments. So some of the building blocks that's produced include essentially include amino acids, which are the building blocks of proteins, and nucleobases, which are the building blocks of nucleic acids, namely, for example, RNA and DNA. So in the same way, if SEPs, and SEP is solar energetic particles, it's important to not get confused between solar proton events, which are SPEs, and these essentially refer to this burst of energetic particles that are being produced, and solar energetic particles refer to the individual particles, namely the energetic electrons and protons. So, if solar energetic particles are a source of energy, could they power chemical reactions leading to the synthesis of biomolecular building blocks? In order to answer this question, what we did is we sort of focused on Earth and Mars around 4 billion years ago. And what you need is a three-pronged strategy. First, you need to estimate the energy flux of the solar energetic particles reaching the surface of a 1-bar atmosphere planet during a single event. Next, you need to find out how many of these events are impacting the early Earth or Mars per unit time. And third, given the energy flux, we need to estimate the rate of production of these biomolecular building blocks. So in order to answer the first part, namely what is the amount of energy being deposited during a single solar proton event, what we did is we sort of carried out simulations involving essentially numerical solutions of the Boltzmann equation to see what flux reaches the surface of. So we focused mostly on Mars in this particular study. And the thing is, a lot of the conclusions carry over to Earth as well, which I won't be going into here. So we sort of essentially estimated the flux of these energetic particles reaching the surface for both current and ancient Mars. And what we find is that particles with energies roughly over 150 MeV can make it way all the way to the bottom on current Mars, whereas on ancient Mars, that threshold is raised to around 3000 MeV, and MeV is mega electron volt. And the reason it's a lot higher for ancient Mars is because we took an atmosphere of roughly 1 bar, which is consistent with the available geological evidence. And so therefore, this essentially enabled us to find what the flux of these particles reaching the surface. I mean, how many particles reach the surface and how much energy is being deposited on the surface. For step 2, in order to estimate the frequency of these impacts per unit time, well, obviously we don't have any direct data of how frequently the sun was producing these solar proton events. So what we did is we looked at the available Kepler data for young sun-like stars, and from that computed the frequency. And by combining step 1 and step 2, we found the resultant energy flux associated with these energetic particles, and it's at least 2 orders of magnitude smaller than any of the well-known prebiotic energy sources. So I mentioned this famous experiments in the 50s which use lightning as the energy source. And then ultraviolet radiation is another that has gained a lot of prominence in recent times. And the resulting energy flux is uh, at least a few orders of magnitude smaller than any of the other sources documented in the literature. And therefore, this sort of brings us to the question, if the energy flux is small, should we even care about this particular pathway? And this leads us to the missing component, namely the third step. And the third step essentially is essentially related to finding what are the yields of these biomolecular building blocks that are being produced. In order to compute the yield, you essentially need to look at the efficiency of this particular pathway. I mean, what is the yield of these molecules per unit energy that is being input. And it turns out that this particular pathway of synthesizing these building blocks from energetic particles has an unusually high efficiency. And so what we did is we basically use laboratory experiments that have already been performed to compute the yields of these amino acids and nucleobases on Earth. And it turns out that the production rate, so this is measured in units of the mass per unit time. So the total production rate of amino acids is around 10 to the power 7 kilograms per year, whereas for nucleobases, it's 3 orders of magnitude lower. So, of course, one has to compare these with other channels. And one of the most prominent channels, one of the most prominent hypotheses that is discussed in the origin of life community is that the meteorites transported these amino acids and nucleobases, and they basically deposited them on Earth. And people have computed what the yields were for these particular pathways. So you can see from this particular slide that the yield of these by building blocks is several orders of magnitude higher for solar energetic particles when compared to meteorites. For example, if it's 10 to the power 7 kilograms per year, we can see that here it's around 300 kilograms per year. And similarly for nucleobases, if it's 10 to the power 4, here it's on the order of 1. So it's nearly 4 orders of magnitude higher when it comes to synthesizing these particular building blocks through solar energetic particles. So this, of course, compares it with meteorites, and it basically looks at how these meteorites are being, basically compares them against meteorites. And similarly, one can do the same thing and compare them with ultraviolet radiation or with lightning and with other pathways. So what we find is that in most cases, the yields of these particular building blocks is either at least comparable or slightly higher than what is being produced by ultraviolet radiation and by lightning. So one can also carry out a similar procedure for Earth-like planets around other stars. And when it comes to planets around M-dwarf, for example, Proxima Centauri, which I mentioned earlier, and TRAPPIST-1, the yields are further boosted by nearly 3 orders of magnitude. And a lot of it has to do with the fact that these particular planets are situated much closer to the host star, and therefore they would receive a much higher flux of these energetic particles, because the flux to leading order kind of falls off as 1 over r square. And it's not strictly true because there's some deviations from it. But to understand it in an intuitive way, you can think of it as roughly 1 over r squared. So if you were to place a planet much closer to the star, you would see that the flux would be increased. So this is quite interesting because on M-dwarf, because these are smaller stars, cooler stars, most of the radiation is actually in the infrared, and these particular M-dwarf exoplanets, they actually don't receive enough radiation, UV radiation for prebiotic chemistry. So in principle, perhaps these solar energetic particles could, ameliorate this particular deficiency. However, a lot more research is required on this front, namely in the form of lab experiments involving atmospheres of different compositions, so basically varying what gases you have and also varying the surface pressure. So that's sort of the second part of the talk. And now I come to the third part. So as we saw, solar energetic particles, I mostly talked about them, or stellar energetic particles basically. I talked about them in the consequence of how they could aid in in prebiotic chemistry. But now we have to look at the other side of the coin and examine whether there could be some kind of negative impact. And so, therefore, the question is, are these solar proton events only a force for good? I mean, that is to say, are they only going to produce positives, or could they also give rise to negatives? And so the thing that I'll be talking about is ozone depletion in this particular context. So there have been a lot of observations since the 1970s and even a bit before that have looked at how the solar proton event, how do they interact with Earth's atmosphere, and what happens when they collide with Earth's atmosphere. And what people have found is that they are known to trigger the formation of nitrogen and hydrogen oxide species, so NOx and HOx as they are called. And these oxides can in turn react with ozone and cause the depletion of ozone. So just to give you one particular example, here you have nitric oxide, I know that combines with ozone O3, and then therefore the ozone is being depleted, and it's resulting in the formation of NO2 and O2. And this particular ozone depletion has been confirmed for solar proton events reaching back to more than half a century. And so let's just consider the scenario where you were to lose all of the ozone layer. Let's sort of imagine hypothetically what would happen if we completely lose the ozone layer. Well, it turns out that if you lose the complete ozone layer, what would happen is that the UV fluxes that can cause damage to biological organisms reaching the surface can increase by a factor of 10 to 100. The reason this is called the biologically effective UV flux is that you have to sort of essentially take into account that different radiation at different wavelengths can cause different degrees of damage. So one has to essentially, in mathematical terms, you have to convolve the flux, or rather the spectral energy distribution with something known as the action spectrum, which measures the degree of damage as a function of the wavelength. And with the gist of the whole argument is that if you were to suddenly lose an ozone layer, the amount of ultraviolet radiation that you would be receiving would increase by a factor of 10 to 100. And other consequences, negative consequences that have been associated with solar proton events include acid rain, which essentially results from the formation of these nitrogen oxides, which react with water and form nitric acid, and then that nitric acid is essentially deposited on the surface of the planet, as well as temperature fluctuations. So moving to keeping with the theme of this ozone depletion, what we did is we looked at the known scalings for what kind of correlations are observed between the degree of ozone depletion and the solar energetic particle fluence And the fluence is essentially the flux integrated over the interval over which this event occurs. And the correlations between the flare energy and the SEP fluence to determine a phenomenological relation in the form of a power law. So this essentially what you have on the left-hand side essentially measures the degree of ozone depletion. And what we have on the right-hand side tells us how does that degree of ozone depletion depend on the uh, energy of the flaring event that essentially gave rise to this particular depletion by way of producing a solar proton event, as well as the distance from the star where the planet is located. So let's say we sort of set DO3 to be 100%, nearly 100%, and ask what is the energy that is required. What we find is that the required energy is around 10 to the power 29 joules for a planet at 1 AU. And so then, of course, we can ask, firstly, is a flare energy of such a large value even possible? And again, by just using some simple arguments, we sort of showed that it's at the upper threshold of what is theoretically realizable. And there are actually empirical observations as well, which show that the highest observed flares on sun-like stars do have energies of roughly 10 to the power 29 joule. And in astrophysics, it's common to use CGS systems. So this essentially means 10 to the power 36 ergs. And just to give you a comparison, the Carrington event that I referred to had an energy of upward of 10 to the power 32 ergs. So this particular energy is around 3 to 4 orders of magnitude higher. So for sun-like stars, again, looking at the Kepler data, we found that superflares of this magnitude might occur once every 10 million years or so on the sun. And of course, this discussion implicitly dealt with an Earth-like planet at 1 AU and therefore around the sun-like star. But then this particular issue of ozone depletion is more prominent for M-dwarf exoplanets. The reason being is twofold. First, if we go back, we see that if you decrease A, then you essentially increase the ozone depletion here. So in other words, you need a lower energy to cause the same degree of depletion if the planet is situated closer. And this is indeed the case for M-dwarf exoplanets. So therefore, you can have almost complete ozone depletion occurring at 10 to the power 26 joule, which is only 10 times more than the Carrington flare, roughly. And moreover, as I mentioned towards the beginning of the talk, M-dwarfs are known to flare more often compared to sun-like stars. So on this note, simulations have shown that total loss of ozone layer can occur within around 10 to the power 5 years, provided that one Carrington type event occurs around once every 10 days. And this is essentially was done for what is known as a moderately flaring star, which means that you can have stars that are quieter and don't produce flares so often, but you can also have stars that are even more active and in which case this depletion time scale would be even lower. So that and so of course, as I mentioned earlier, you can have complete ozone depletion for flares of a certain energy, and this particular flares in principle could occur once every 10 million years or so. And if there was complete ozone depletion, the Earth would be bathed suddenly in very high doses of ultraviolet radiation, and in principle, it could lead to large-scale extinctions of biological organisms. And so then the question is there some kind of a fossil record that reflects such a thing? And so this has been done since the 80s. And paleontological data shows kind of quasi-periodicity in the extinction record. and there's a rough period of roughly 26 million years. Some other studies have tended to shift it a little bit more. I mean, for example, there was subsequent study that suggests that the rough periodicity is around 62 million years. So but you can see that it's on the order of tens of millions of years. Now, a number of different explanations have been advanced to explain this observed periodicity. So there's a lot of explanations ranging from all kinds of geological factors to factors involving the solar system as a whole. For example, how could slight changes in the eccentricity, obliquity, etc., affect these things? And then there have also been a large number of astrophysical explanations which try to explain this periodicity in terms of the sun is moving around the Milky Way, and at some points it could go through denser regions and when it goes through a particularly dense region, the outer solar system could be perturbed, and for instance you could have comets coming and impacting the Earth. So that's one example of a hypothesis that has been put forward. And of course, as I mentioned, you can have solar flares of this particular energy, 10 to the power 29 joules, occurring on the order of once every 10 million years or so. So perhaps in principle, you could have mass extinctions being produced by flares of this magnitude. And then, of course, the question would be, how do we distinguish between the various hypotheses? In other words, can we identify some kind of distinct signatures that would arise from flares as opposed to those arising from other astrophysical phenomena or just due to volcanism or other such factors? So I won't be talking about all these factors here. I'll just say for the time being that there's many, I've listed 4 of them here, but there's at least 2 or 3 more. And in principle, if you were to find some particular extinction that sort of checks all these boxes, and then there would be a good chance that it could have been driven by a solar superflare. And so, for example, just one of them is the prediction is that the extinction probability, which means the fraction of species that went extinct as a percentage of the total species at a given latitude. So what we predict is that you would see a higher fraction of species becoming extinct at higher latitude. So in contrast, the opposite trend is expected to occur for the current ongoing Anthropocene extinction, which is being driven by current climate change. And then there's a few other factors which I've listed here and I won't be going into. And the last part, I'm just going to talk about it for 2 or 3 minutes. I won't be going into it in much detail. So far, of course, I've talked about the risk to life, but life, of course, essentially meant implicitly non-technological life, essentially biological organism. Now, I just want to spend a little bit of time talking about the risk to human technology. And there are quite a few risks that are posed by these coronal mass ejections and so on. And so there are risks posed to human space exploration, to satellites, to communications, aviation, and electric power. So, for instance, the geomagnetic storms, which are essentially disturbances, fluctuations in the Earth's magnetosphere, which would be caused by these coronal mass ejections impacting the Earth's magnetosphere and sort of compressing it and sort of causing perturbations to it, would result in geomagnetically induced currents. And these currents are capable of disrupting power grids. And it's believed that they could cause large-scale failures that may take weeks or even up to years for full repair. And of course, without lack of electrical power, one would see, a breakdown of supply chains, food production, etc. And the widespread damage to satellites is expected. At least around 10% of all satellites could end up becoming completely inoperational, and the rest would experience damage. So this has been studied to some degree in the 21st century, and it's estimated that the total worldwide damage for a Carrington type coronal mass ejection impacting the Earth. And this Carrington type event, just to reiterate, was the largest in the industrial era. And when it happened in 1859, telegraph communications were disrupted throughout the world. And at that time, we had much lesser technology, and we were less dependent on it compared to today. And anyway, if you were to have a similar event occur now, economists have forecast that the total damage would be on the order of 1 to 10 trillion US dollars. And so we sort of looked at how does one see whether this risk is being sufficiently addressed. And again, I won't be getting into this particular aspect, but all I want to say here is that the current expenditure that is being, the current amount of funding that is being invested to sort of model these flares and to predict them, and then to also take measures against making our society more resilient, it's not sufficient by orders of magnitude. And therefore, there is a need for investing in better predictive models and better instruments for detecting early signals of it. And then, of course, trying to harden electronics and power systems, and potentially even setting up some kind of deflectors in space, which we discussed in a work that I think I haven't cited here. So that sort of essentially completes my talk. So I have a few basic take-home messages to mention. The first is that flares and coronal mass ejection can, in tandem together, they can increase the atmospheric escape rates transiently by a few orders of magnitude due to the higher radiation associated with flares and the higher masses of plasma that are being expelled and that are basically impacting the planet due to the coronal mass ejection. Secondly, solar energetic particles may represent a promising channel for synthesizing prebiotic compounds, especially when it comes to M-dwarfs, because they don't receive enough ultraviolet radiation, and therefore we may have to look at other channels. Thirdly, solar energetic particles, they're not always guaranteed to have only positive effects. They could, in principle, give rise to ozone depletion, and they might therefore have the capacity to trigger a large-scale extinction. And of course, to understand whether this is feasible, what we need to do is to comb through Earth's fossil record and to look for the smoking gun signatures of the type that I mentioned. And then lastly, the risk posed by large flares and by large space weather events are quite significant. And even though there has been increasing awareness of this issue, we are still far away from investing enough effort and funding on this point. And seeing as how we are now currently living in a very turbulent era, it's important that we take such risks into account and try to mitigate the impact of these risks in the current era. And that brings me to the end of my talk. And I would like to thank you all for taking part in the talk. Thank you. And I'll be happy to take questions.
Thank you, Manasvi.
Thanks a
a lot.
Manasvi.
Thank you.
Yeah, that was a great talk. You covered a lot of topics in such a short time.
Right.
And yeah, very informative. So, Srini, do you have any question?
I have one question, which is sort of very generic and probably important. When making any estimates of SEP or lightning, etc., in forming a prebiotic material,
Right.
usually one looks for some average estimates. There is so much energy being deposited, etc.,
Right.
etc.
Right.
But what we know from nonlinear systems is that there are very large excursions from the mean value. For example, if you look at, let's say, dissipation events in the turbulent atmosphere, you can get events that are tens of thousands of times larger than the average value.
Right.
In some sense, it is important not to just look at the average values, but excursions from the
Right.
average.
Right.
And I wonder if such things have been ever taken into account in making estimates like this.
Yeah, I think that's a great question because yeah, it's usually indeed assumed that the mean is sufficient, but you can definitely have fat tails and things like that where
Yeah,
you would definitely want to look at these deviations as you rightly pointed out. And the thing with nearly all the phenomena that I've described, apart from ultraviolet radiation, which is more or less a steady state thing because the sun is this luminosity is changing very slowly. But when we take lightning or so these solar proton events, these are by nature impulsive phenomena. And so, yeah, averages are definitely a crude, these are definitely order of magnitude estimates in the spirit of, order of magnitude
yeah. No,
astrophysics.
I
But
understand. I
yeah,
understand
but
that. Yeah.
I think, but your point is very valid. I think we should definitely be paying more attention to the outliers and
Yeah, I think
yeah,
so.
yeah,
Because even within a solar flare event,
right,
which is already an outlier,
right,
there will be regions, localized regions, both in
right,
temporal and
right,
spatial domains,
right.
which are very intense compared to the average effect. And that's
Right.
my main point.
Right, right, absolutely. I think that's a very good point, and that's why I mean we sort for a lot of these studies we use the Carrington type events as
Yeah,
a template,
yeah,
but
yeah.
for sure you can have more extreme value events that are like many orders of magnitude higher, and there's been very little effort invested. I mean, Dr. Atri has done some work on that front, but in general, I would say solar proton events have not been studied to the degree
Yeah.
that they warrant, and certainly not many have studied these kind of extreme events that are, I think, definitely necessary for future work.
Yeah. Thank you very much. Yeah.
Yeah, thank you.
Yeah, one problem here with proton events is that proton beams are very expensive,
Right,
and
right,
so all the experiments are done with low energy protons
exactly,
at a fixed
exactly.
energy,
Right,
and
right, right.
those
Absolutely,
heats are obtained using those, and
absolutely.
so that is certainly an issue.
Yeah, absolutely. I mean, I didn't, of course, put all the caveats in, but that is one of the most prominent caveats. Namely, we don't know how the yield scales with the energy. We essentially use the 10 MeV particles, but what we are really talking about are particles. I mean, the particles that penetrate to the surface are more often than not going to have energies upward of 100 MeV. So there's definitely I mean, and again, I think this sort of goes back to the question that Professor Srinivasan raised, namely, these would be nonlinear phenomena. You could have cascading and so on. And I think the yield, in some ways, I think our estimates were actually somewhat conservative because we
Yeah.
were using yields that were probably a bit lower. And yeah, so I think that's a very good point, Dr. Atri. It's one of the big caveats is we you would definitely want, and that's why I did mention briefly that you do want I mean ideally more laboratory experiments looking at the 100.1 GeV to 1 GeV range.
Yeah.
Yeah.
Dimitra, there are some questions on the Q&A.
Yeah, I'm going over. So there is a question by Robert, so I'm going to allow you to talk. Go ahead.
All right, thank you. I thought talk was great. I've just got a question about again about the model. I guess talking about. Did you make any assumptions about whether the planet had a magnetic field or not? I just thought that if you have one, the lower energy protons are going to be deflected towards the poles, which which would probably mean less biotic compound production. And did you include that or not?
I think that's a great question. Thanks for bringing it up, Robert. So we did the cases with both magnetized and unmagnetized Earth and Mars-like world, and it turned out the differences were not very significant, especially in the context of the other caveats which we have already gone over with Dr. Atri and Dr. Srinivasan. But we did test both the cases, and the reason we didn't see a very big difference in the energy flux deposition at the surface is a lot of the particles that penetrate through and reach the surface are really being slowed down by the atmosphere more so than the magnetic field. So if you look at the Larmor radius of these, the deflection that would arise from planetary fields is quite minimal because these particles are such high energy that they aren't really very significantly being bent away by these planetary magnetic fields. So we took an unmagnetized planet, which essentially means no magnetic field, and then we took one with an Earth-like magnetic field. Now, of course, in principle, you could consider planets with magnetic fields that are orders of magnitude stronger than that of Earth due to some kind of an unusually vigorous dynamo. But we didn't look at that particular class of planets, but we did compare the unmagnetized and Earth-like magnetic fields.
All right, thank you.
Thank you.
Yeah, okay, we have another question by Mohammed Taha. I will let you speak. Yes, Mohammed, go ahead.
Maybe he's not
Hello.
there. Okay.
Thank you for the presentation. My question is there any theoretical measures that we can do to prevent any effects of the super flares from the sun? I mean, can we protect ourselves and the planet from such effects that the professor presents in his presentation? Thank you so much.
Yeah, thanks for your question, Mohammed. The short answer is yes, but it requires quite a bit of revamping. So the power grids are essentially at the core of all the economic and other damage that is predicted, because if you lose your electricity, we all know how much the modern world depends on it. And so there are ways to certainly make them more robust, to essentially harden these electronics and to essentially revamp power grids and make them more smart in a way. And for instance, Europe's power grid, for various reasons that I won't be getting into right now, are somewhat better adapted to withstand these kind of space weather phenomena compared to the US power grid. And certainly there are more exotic solutions. So we sort of did what in physics you would call a Gedanken experiment, a thought experiment, where we were trying to look at placing a large magnetic deflector in space that would deflect the bulk of these plasma. And then we tried to do some simple estimates for what cost it would entail and whether it would be mechanically feasible and so on. And well, the cost turns out to be around $100 billion, which is very, very expensive. It's comparable to that of the International Space Station, but in principle, it could certainly deflect the bulk of these particles, and 100 billion is 0.1 trillion, and the economic damage we are looking at is on the order of 10 trillion or so, or a factor of few lower. So I would say there are definitely different solutions, starting from at the Earth level all the way to potentially implementing some solutions in space itself. So I think the short answer would be yes, and the long answer would be that you have to kind of look at it at a system by system level. Thank you.
Yeah, thank you very much. This is great. Yeah.
All right, so if there are no more questions, let us thank our speaker again. Thanks a lot, Manasvi.
Yeah.
And see you everybody next week.
Okay,
Thank
see
you.
you.
Okay,
Bye.
yeah. Thanks for having me, and yeah, it was a pleasure to be
Okay.
here.
Look forward to seeing you again soon.
Right. Thank you so much.
Okay. All
yeah.
right. Bye.
Right. Thank you.
Thank you. Bye.
All right. Bye bye.